In this video we're looking at a special type of two-dimensional motion called projectile motion, and this projectile motion we're looking at is going to be, in particular, a horizontal projectile. A horizontal projectile is a projectile that is launched with 0-degree launch angle, meaning it's just launched horizontally. It describes a parabolic trajectory, as the example with the yellow billiard ball that is struck at the same time that the red billiard ball is dropped from the previous video, or the free fall video. Except in this horizontal projectile, we're actually going to go through and analyze each part of the projectile's motion in the x and y direction and figure out what types of values we can solve for. So, this is a type of 2D motion. We have 0 launch angle for a projectile, so I have a Nerf launcher there that's, say, at the top of a table, though this could be something like a ball is thrown perfectly horizontally off the edge of a cliff. Anything like that that's set up as a problem in the AP exam is going to indicate that we have a horizontal projectile. So just remember that the 0 launch angle, if something is going right over the edge parallel to a table or a cliff, that indicates a horizontal projectile setup. I have my T-chart that I'm going to organize at the bottom left with my X and Y parts of motion. Part B I have over here of stuff we need to remember. Y direction is free fall in projectile motion. So everything that's happening in the blue or Y direction is just going to be the same as my free fall analysis, where the acceleration in free fall is g. The final velocity, or really any velocity during that free fall, is changing, so the final velocity is not going to be the same as the initial velocity in the Y direction. And because it has a 0-degree launch angle and it's just shot off horizontally parallel to the table, its initial velocity in the Y direction is going to be 0. That's a very important thing about horizontal projectiles. We know that the initial velocity in the y direction is 0. In the x direction, we have a constant velocity. It's not changing. That means our acceleration in the x direction is 0. So here is just like in free fall, we're assuming that gravity is the only force acting on this object. There's no air resistance. So whatever speed with which it leaves the projectile launcher in the horizontal direction, it keeps that speed during every increment of time until it hits the ground and is stopped. So it has 0 acceleration in the x direction. That means that every point along its motion in the x direction, it has the same velocity. So its initial velocity in the x direction is equal to final velocity in the x direction. And its initial velocity in the x direction is never 0. If it's 0, then it's just being dropped straight down, and it's just like a normal free fall problem. I'm going to draw in our floor there and some dots to indicate the trajectory of this projectile, and then I'm drawing in pink some times, T0, T1, T2, and TF for T final when it finally strikes the ground. Whenever projectile problems or other problems are asking about what's the final velocity, for instance, of a projectile, and it's about to hit the ground, they mean right as it strikes the ground. Problems should be worded clearly enough so that that makes sense, that's indicated, that's known, but sometimes students think that it starts from 0 before I pull the trigger, 0 velocity, and it ends with 0 velocity because I hit the ground. Well, no, that's after another event takes place. The ground exerts a force back onto the projectile and actually causes it to accelerate in the opposite direction and slows. That's a whole other set of kinematic activities that are happening. When we're talking about the projectile, we're talking about it starts with some initial velocity, like this one's just going to have a velocity in the x direction, and then as it's projected along this trajectory, gravity is acting on it, and so we have a gravitational acceleration, and a final velocity would be at TF right as it hits the ground. It has some non-zero velocity. I've indicated my launch angle is 0 degrees up there. And that just means I'm measuring from the positive x direction. There's my cheat chart I'm drawing up with my kinematic variables with the subscripts to indicate which direction I'm talking about. I'm going to fill in those things that I know so far. I know the acceleration in the x direction is 0. That's always the case for projectile motion. I have initial and final velocities in the x direction that are just going to be the same number. And once I find out what that number is, it's the same velocity the whole time. My delta x I don't know right now, and time I don't know, but I know it's the same in both directions. Acceleration in the y direction is g, so that's directed downwards. In this case, it'll be minus 9.80 meters per second squared, because notice I defined my directions next to my diagram. My initial velocity in the y direction is 0. We mentioned that because it's being launched perfectly horizontally, so it has no velocity in the y direction. If I shoot it downward, then it does have an initial velocity in the y direction. If I shoot it upward, then it does have an initial velocity in the y direction. It'll just be negative or positive, respectively, depending on if my angle of incline for my projectile launcher is positive or negative. In this case, it's perfectly horizontal, so I have 0 initial y velocity. My final y velocity is going to be some number. I don't know what that value is going to be yet. And delta y is going to be that vertical displacement or the height, whatever I fall through. I don't know that value yet either. I'm going to draw in some vectors that are going to represent the horizontal velocity in red there. So there's my Vx, my velocity in the x direction is in red, and those values are just copy-pasted vector arrows at increments of time t0, t1, t2, and t final. Notice they're the same magnitude, so all of these have the same value. The acceleration in the x direction is 0. What else now? In the vertical or y direction, I have initial y velocity that is 0, so I have no vector drawn there. As time goes on, though, I know that I have an acceleration equal to g directed downward, so my velocity in the y direction increases at a constant rate. That rate is g, and so I have velocity in the y direction sub 1 to indicate at t1 I have vy sub 1, and then I have vy sub 2 at t sub 2, and vy sub f for the final y velocity there at tf. My delta y and delta x indicate displacements, and since it's a two-dimensional motion, we are looking at the two displacements separately, just like I've drawn the two different direction velocities separately. So my delta y in turquoise, or teal, that's the vertical displacement of the projectile from the place it was launched down to the ground. So in this case, it's pretty much the height of this table it's being launched off of, but I'm careful to make sure that that height includes where the actual projectile itself starts. So in my diagram, it's technically a little bit above the top of that table. That's my delta y, and it'll be a negative value because it moves in the negative direction, downward, because down I called negative. Delta x is also referred to the range in projectile motion, and you can see the range there is just the horizontal displacement. There are three things I want to be able to find out. One, how long until it hits the ground? That's the time value I need to know. Two, where will it land, or what's the range? That's an important thing for me to be able to figure out for horizontal projectiles. And three, with what velocity does it hit the ground? And by that I mean the final resultant velocity. That's going to be at some diagonal, some angle, and there it is in green. So these three things that I think we need to be able to find out, we're going to identify on the next slide. How long it takes to hit the ground, that's finding that delta t, or the t final minus t initial. How much total time elapses from the time it's launched to the time it hits the ground. Where did it land? What's the range? That's that delta x question. With what velocity does it hit the ground? That's the matter of finding the magnitude and direction of that final resultant velocity vf in green. Let's take a look. As I redraw some of this, we're going to go through each one of these things. We're going to start with how long it takes to get to the ground. So that's a matter of a difference in t's or times. And let's name a couple of things that we know. A, in the y motion, that's free fall. I know that. I know my initial y velocity is 0. And I know from my kinematic equations that the displacement in the y direction is equal to the initial velocity in the y direction times time minus 1/2 g acceleration due to gravity times the time squared. This is one of those special cases where it's very nice how the initial velocity in the y direction is 0, and that simplifies my equation. That part goes away, and I'm just left with the following. Now I have an equation that relates the displacement in the vertical direction downward to the acceleration due to gravity and time. I can solve this for time. Be mindful that my displacement's negative, so I have that minus sign go away. And I end up with a square root value, a square root of a positive value, which gives me my time. So whether it's free fall and I just drop the object there where the Nerf gun is, or I project it horizontally, and horizontally is important here because it has 0 y velocity to begin with, I'm going to end up with a time value that's right there, the square root of twice the height over g. That's how I can find the fall time, how long it takes to hit the ground. Number 2, where will it land? That's asking what the range is. So as far as the range goes, the delta x, what do we know? A, we know that the velocity in the x direction is not changing, and B, what amounts to the same thing, the acceleration in the x direction is 0. That's real helpful. We can use the following equation here, delta x equals v naught, or initial velocity in the x direction times time, plus 1/2 acceleration in the x direction times time squared. Because we just said that the acceleration in the x direction is 0, that part of that equation goes away. And this simplifies to simply distance equals rate times time. So for us, delta x equals v naught in the x direction times t. But the velocity in the x direction is unchanging. It's always the same. So I can just write delta x equals velocity in the x direction times time. And I just solved for time. So if I know the height and the acceleration due to gravity, and I always know the acceleration due to gravity, then I can solve for what the range of this projectile should be. Number 3, I'm asking, what's the final velocity in our projectile problem? Well, that's going to be the resultant velocity of those two Vx final and Vy final of the projectile. Those are illustrated there at the very bottom at time t sub f. The two parts that I need to be able to do here are find the magnitude and the direction of the vector. So first I got to ask, okay, what is Vx final and what's Vy final? Vx final I already know is just from that distance equals rate times time, or that portion that I have written in number 2's box there, delta x equals v naught times t. If I solve that for Vx, then I'm going to have delta x over t, or the displacement in the x direction divided by the time. That'll help me get the velocity of the x in the x direction, or the final x velocity, if I don't have it given to me in the problem already. As far as the y velocity goes, I could use my couple of kinematic equations to determine what the final velocity in the y direction is. And remember, it's just as if it was in free fall by itself and we just dropped it. So the initial velocity in the y direction is 0, so I could use that one equation, v final y equals v initial y minus gt, where the initial y simplifies to 0, and I just have the final velocity in the y direction is equal to minus gt. I could substitute in the value I found for t earlier if I need to. Also, I have another box equation at the bottom that's from the final velocity squared equals initial velocity squared minus twice the acceleration, in this case little g, times the displacement delta y. I can solve this one for final velocity in the y direction. I get square root 2g times delta y, which is the same as the square root twice the gravitational acceleration times the height it falls. Remember, this is a value that could be plus or minus when we have those radicals, so this would be a good example of that time where I would have the square root of a positive value that then I would have to decide whether it should be positive or negative. In this case, that value would need to be negative because downward is negative, and this is a final y velocity. Notice there at number 3 up in the top right, I've finally said, okay, to get the final value for yf, I need to do my Pythagorean theorem to find the magnitude of vf, or the final velocity, and that involves knowing both of those final velocities in the x and y directions. Then to find my angle, which in this case I would measure as a negative angle, I would use my arctangent function, because I feel like that's the simplest way to do it based on what I probably have, and that's going to be the arctangent of that ratio of the final velocity in the y direction in blue, divided by the final velocity in the x direction in red. Look at an actual problem here. This is from our Cutnell-Johnson book. It's a very straightforward, pretty simple problem compared to the literal equations we just manipulated in the previous slide. But this is an example of a plane that's flying at a perfectly horizontal direction, so this is going to be a horizontal projectile problem. It releases a care package at some time t0, I suppose, and this care package has a known velocity, the same as the forward velocity of the plane, and that's our velocity in the x direction. As it falls, its velocity in the y direction increases. So here, as the problem depicts, a cargo plane drops care package as depicted. Determine the magnitude and direction of the velocity of the package as it strikes the ground. Assume air resistance is negligible and g is 9.80 meters per second squared. I'm going to highlight and box some things that I know about the problem already. Specifically, I know that the velocity in the x direction is at 115 meters per second. I have a vertical displacement in the blue box that's a minus 1,050 meters. And I have some other values. The initial y velocity is 0, and the acceleration in the y direction is g, directed downward. So I identify what it is I'm looking for. I'm going to need to find the final velocity of the care package, that's green vf, and that means I need to find vx final and vy final, the two components of that large vf in green vector. I have my t-chart over there that I can fill in with the values that I know, and then I need to start identifying what I want to solve for next and what kinematic equation is going to help me do so. I've decided to find the velocity in the y direction final by using vf equals minus gt, because we have a 0 initial velocity in the y direction. Remember those simplified free fall equations. I need to know the time here because the time isn't given, so I use my other kinematic equation, delta y equals minus 1/2 gt squared, in order to find the time. We found that on the previous slide as well. I can substitute that value of t, the square root 2 delta y over g, in for my pink t in equation set number 1 there on the left. You notice that one set of my g's cancel out and I end up with a final y velocity that is equal to the square root 2g delta y. That should look familiar. Substituting in values for this, I can get a final result that is final velocity is plus or minus square root of some number, which happens to be 143.46. I need to choose a negative value for this because this vector is directed downwards, and downwards defined as negative in the problem. So, in writing in my final answer on the right, in my t-chart, I'm writing in a rounded value of 3 significant digits of minus 143 meters per second because the data that I was provided with in the problem has 3 significant digits in the smallest case, or fewest number. Part 2, I just feel like solving for time, I suppose, here, since I already have the equation up there. So now, here I know what the time is that it takes the package to hit the ground, and knowing these other kinematic variables also helps me check my work in previous parts and develop more confidence in my final answer. In order to get to the final velocity, we also need to use our Pythagorean theorem here, or some other trig methods, to get at the actual magnitude of that green final vector, velocity at the bottom right of the diagram. I've done here the Pythagorean theorem, the square root of the velocity in the x direction, which was given in the problem, and my newly found velocity in the y direction. Summing those squares and then finding the square root produces a result of 183.51 meters per second. This is going to round to 3 significant digits because I have 3 significant digits I need to round to. And then in finding my angle, because the vector requires a magnitude and a direction, the angle there I decided to use the arctangent with the opposite and adjacent sides of the triangle being the final velocity in the y direction and final velocity in the x direction respectively. And that produced an angle of minus 51.2 degrees. Always go back and look at your picture and see where that angle should be based on what numbers you use, and make sure you're using your plus or minus sign for your angle reading appropriately. The arctangent function doesn't produce all the desired results in every quadrant, only 2 of them, so just be mindful of that. Always go back and check the physical reasonability and geometrical reasonability of your results. So I have a final velocity now, 184 meters per second, at an angle of minus 51.2 degrees. I can check the reasonability of that. If it's at minus 51.2 degrees, my vertical or opposite side of this triangle should be larger than the adjacent, and indeed 143.46 is longer than 115. And 184 meters per second, that hypotenuse value is larger than both of my opposite and adjacent sides. So geometrically this makes sense, and physically for the package following that distance and at that initial velocity, we've seen an increase in the y velocity because it started from 0. That makes sense, and we have a larger resultant v final than our initial x or y's. So that sounds good. Lastly, we're going to point out the range there is the last thing I can fill in on my t-chart. And that range is, again, like we said, it's basically a distance equals rate times time problem. That horizontal range is this displacement in the x direction, just like the analog to the delta y, which is simply the height the object fell from the airplane. The delta x there I can solve for with vx times t. So the velocity in the x direction, which stays constant the entire time, is 115 meters per second, times the amount of time that it was moving at that horizontal velocity, which was 14.6 seconds, produces my delta x, or displacement in the x direction, which is 1,680 meters if I round it to 3 sig figs. There I have a value for how far that projectile moved, or what its range was. So this would be very important, a good number to know if you were actually dropping a care package to somebody, or especially if it was on an island and you needed to make sure it landed on the island and didn't overshoot and get lost in the water. What range are we going to achieve based on our current airspeed and our height, which also determines the fall time for that care package. When we come back, we'll look at, in the next video, projectiles launched at an angle. And then we'll do some more review problems after that. That will be a lot of 2D motion problems, kind of the way the AP free response questions tend to look.